Hello dear friends, I am Professor BJTs going to teach you regarding BCD to decimal decoders. This is our lecture number 3. BCD is abbreviation for binary coded decimal. That is, it means that it is not actually binary, but it is coded in the binary numbers, 1-0 forms. Because the digital system can understand only binary numbers, that is 2-state devices, so it is written in 1-0 forms, that's all. Otherwise, it is actually the decimal number itself. The BCD code expresses each digit in a decimal number by its nibble equivalent. So, you are having a decimal number. That decimal number, from that decimal number, each digit is converted into nibble equivalent of binary. For instance, if you want to convert a decimal number 3, what is the binary equivalent of that? In nibble means group of 4 bits. So, it should be converted into 0011. Similarly, for instance, if it is made from more than 1 digit of binary number, then each decimal digit should be converted into nibble equivalent. Like this. For instance, decimal number 4 to 9 is changed to this BCD form as follows. Here I am just putting it separately. The decimal number was 4 to 9. Each digit 4 is converted into 0100. 2 is converted into 0010. 9 is converted into 1001. To anyone using the BCD code 0100, 0010 and 1001, that number is combined, is equivalent to 4 to 9. As any another example, let us say 4 number 8963 is decimal number. Here each digit is converted into nibble equivalent. 8 is converted into 1000. 9 is converted into 1001. 6 is converted into 0110 and 3 is converted into 0011. Again, we have changed each decimal digit into its binary nibble equivalent. Why this is done? What is the reason? Some early computers process BCD numbers. So, initially, arithmetic operation was performed in BCD numbers. They were not having, like what we are using today, is your 2's complement arithmetic, etc. It was not there. Initially, it was started with BCD numbers. This means that decimal numbers were changed into BCD numbers, which the computer then added, subtracted, etc. The final answer was converted from BCD back to the decimal number. So, previously, the computers were processing BCD numbers for arithmetic operations. So, we were converting into the BCD numbers, then it will fetch to the computer, computer performs its job, and then again it is converted from BCD to decimal number. That way the process was complete. Here is another example how to convert from BCD to its decimal number. Again, the same way, you just split into the group of nibbles like this. 0101, this is a nibble. The decimal equivalent is going to be 5. 0111, decimal equivalent is 7. 1000, decimal equivalent is 8. So, we can say that 578 is decimal equivalent of 0101, 0111, 1000. One final point should be considered. Notice that BCD digits are from 0000 to 1001 only. The reason is that decimal number is from 0 to 9 only. So corresponding to 9, 1001 will be there. All combination above this, that is from decimal number 10 to decimal number 15, that is 1010 to 1111, cannot exist in BCD code because the higher decimal digit, the highest decimal digit being coded is only 9. Now, BCD to decimal decoders. How this circuit can be prepared? The circuit of figure 4.18 is called 1 of 10 decoder because only one of the 10 output lines is going to be high. So here we have utilized the bus bar system. You will see in this circuit, here we have utilized the bus bar system. Here A and A bar is available through the inverter, B and B bar is available, C and C bar is available, D and D bar is available. And we have utilized the 4 input AND gate, 10 AND gates is going to be utilized because we are converting a BCD to decimal equivalent. BCD is a 4-bit number. So ABCD is a 4-bit decimal binary nibble equivalent is going to be used as the input. And these are going to be the outputs will be there. How it is connected? It is connected to the input of each AND gate just like a fundamental product. For A is equal to 0, B is equal to 0, C is equal to 0, and D is equal to 0. Then A bar, B bar, C bar, and D bar is going to be high. Then output of this AND gate is going to be high. That means Y0 is going to be high. All other outputs remains in the low state. This is the circuit. For instance, when ABCD is supposed to be 0, 0, 1, 1, only Y3 AND gate has all high inputs. You see that here. If A is equal to 0, that means A bar is going to be high. B is equal to 0, B bar is going to be high. C is equal to 1 and D is equal to 1. So these are the 4 inputs connected to this AND gate. So all 4 input of this AND gate is going to be high. So output of this AND gate Y3 is going to be high. So this way, a choosing from 0, 0, 0 to 1, 0, 0, 1, from Y0 to Y9, any one of this output we can make it high, and at the same time all other output remains in the low state. We can take another example. If ABCD changed to 1, 0, 0, 0, only Y8 AND gate has all high inputs. As the result, only Y8 output is going to be high. If you check the other ABCD possibility, 0, 0, 0 to 1, 0, 0, 1, you will find that subscript of high output always equals the decimal equivalent of input BCD digit. For this reason, circuit is also known as BCD to decimal converter. Here, we are not going to prepare such kind of circuit every time in the laboratory using this NOT gate and AND gates because it is going to be complicated. Rather than that, we are going to utilize the IC in TTL form which is already available. 7445 is the IC which is available for converting the BCD to decimal conversions. If you see this IC, pin number, this is a 16-pin IC and it is a TTL. So 16 number pin is utilized for the VCC and 8 number pin is utilized for the ground. Here 8 number pin is utilized for the ground, 16 is for the VCC. VCC how much you have to give? Because it is TTL, completely regulated power supply of plus 5 volt should be applied here only. It can tolerate only 0.25 volt plus or minus from plus 5 volt. So be careful whenever you are using the TTL IC, only plus 5 volt regulated supply should be used. This pin number 12, 13, 14 and 15. They are nothing but BCD inputs. Pin number 1 to 7 and pin number 9 to 11, they are nothing but outputs Y0 to Y9. Typically, you would not build a decoder with separate inverters and AND gates, as shown in a figure 4.18. Instead, you would use a TTL IC like the 7445 of figure 4.19. Pin number 16 connected to the supply voltage VCC, which should be used 5 volt, I just told you, and pin number 8 is utilized for the ground. Pin number 12 to 15 are for the BCD inputs ABCD, while pin numbers 1 to 7 and 9 to 11 are for the outputs Y0 to Y9. This IC is functionally equivalent to the one in figure 4.18, except that the active output line is in the low state. That means, according to the BCD inputs, whichever output is going to be active from Y0 to Y9, that particular output is going to be in the low state rather than in the high state in a previous circuit with AND gates. Maybe inside the IC, it is the NAND gates are utilized, so active output is in the low state. All other outputs will be in the high state. All other output lines are in the high state, as shown in the figure 4.4. Notice that an invalid BCD inputs force all output lines into the high state. Which are the invalid BCD inputs? From 10 to 15, that means 1010 to 1111. That is the BCD input which we have considered as a invalid BCD inputs. And whenever that input is applied as an input, all output lines will be in high state only. That you can see in this truth table also. This truth table represents the working of this 7455 IC. You see that whenever ABCD is going to be L, 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 L. L means low and H means high. Only Y0 output is going to be in the low state because only that output is going to be active. All other output is inactive. So all other output is in a high state. Similarly, when the input is going to be 2, that means LL, HL, 0010, that is decimal equivalent of 2, then only Y2 is going to be active and output of Y2 is going to be low. All other output is going to be in high state. That way, this IC is going to be work from 0 to 9, which is valid inputs. And from 10 to 15, that is HL, HL to HH, these all are invalid inputs. Corresponding to that, all output remains into the high. That means IC is inactive. The decoded output, now there is an example related with this. Just see and to understand this example. The decoded output of a 7445 can be connected to light-emitting diode, LEDs, as shown in the figure 4.20. If each resistance of 1 kilo ohms and each LED has forward voltage drop of 2 volts, how much current is there through the LED where it is conducting? See how the circuit is connected. This is a schematic circuit diagram of IC 7445. ABCD is the BCD inputs. Pin number 16 is for the VCC, that is 5 volt connected. Pin number 8 is the ground connected. Y0 to Y9, that is the output. Here, each one bubble is shown, which indicates that output is in active low state. And that means whenever output is going to be active, that particular output will be considered, ideally it will be 0 volt. So, whenever active output is going to be in the low state, that particular LED is going to be conducting. And that particular LED, that cathode is in the low state, anode is connected with the high state. So, that particular LED is in a forward bias, current will flow through that LED and that LED will light up. all other LED remains in the dark. Now, according to the examples, the resistance connected here is 1 kilo ohms. So, if you consider that this one particular LED is going to be on, how much and voltage drop across this resistance, this LED is going to be 2 volt. So, how much current will be passing through this one? You can apply the Kirchhoff's law. Here, VCC, that was 5 volt, minus ICRL, that is equal to voltage at this end, that is going to be 0 volt. And so, 5 volt minus voltage drop across this one, 2 volt, that is equal to ICRL or IR. And I is you have to find out, and R is known. So, you can put it like that way. 5 volt minus 2 volt, that is going to be 3 volt, divided by 1K, that means 3 milliampere current will be flowing when the LED is going to be forward biased. There is another example is given related to this one. The LEDs of 4.20 are numbered from 0 to 9. Which of the LED is lit for each of the following conditions? A, if ABCD is going to be the first condition, 0, 1, 0, 1. What is the decimal equivalent of this one? 0, 1, 0, 1 means 5. So, the subscript of output, that is Wi-Fi, that is going to be only active. So, that particular LED is going to be light up, all other LEDs is going to be off. Second condition, B, ABCD is going to be 1, 0, 0, 1. Corresponding to that, Y9 is going to be light up because that output is going to be low. So, that LED is going to be forward biased, all other LEDs is going to be off. The third condition, if ABCD is going to be 1, 1, 0, 0, then the corresponding to that decimal equivalent is going to be 12 and it is invalid state. So, none of the LEDs is going to be forward biased because all output remains into the high state. So, none of the LEDs forward biased, all LED remains off. Now, the next important topic is 7-segment decoders. 7-segment display unit, you know that each and every place you can visualize them. This is nothing but the combination of 7 LEDs. They are going to be representing or they are going to be light up in such a way that it will display 0 to 9. A LED emits radiation when it is to be forward biased. Why? What is the reason? What is the difference between LED and normal diode? Normal diode, when it is forward biased, doesn't radiate the emissions, but LED is light emitting diodes. That means it is emitting light when it is to be forward biased. Because the free electrons recombine with the hole near the junctions. So, in LEDs, what happens actually? Near to the junction, that means at the depletion regions, when the electrons are going to be recombined with the holes, that means they are coming from higher energy levels to the lower energy levels and they give up the energy. And that energy will be in the form of either you can say that Hs or Hc upon lambda. That is, H is a Planck constant, C is the velocity of light, or Hc upon lambda, that means lambda is a wavelength or frequency, you can say that. So, corresponding to that particular frequency or wavelength from 4000 to 8000 angstrom, it will fall and hence it will radiate a different kind of lights. That is the way LED works. How that LEDs could be prepared? By using elements like gallium, arsenic and phosphorus. A manufacturer can produce LEDs that emit red, green, yellow, blue, orange and infrared, which is invisible lights. LEDs that produce visible radiations are useful in stress instrument, pocket calculator, etc. And LED uses infrared or invisible lights that is mainly utilized in remote control. All kind of remote control. If you see the TV remote control, if you see your AC remote control or other remote controls, there naturally the LEDs are using IRs. infrared. The wavelength of infrared is normally from 8,000 angstrom to 20,000 angstrom in between. This is the way 7-segment indicator or display unit, you can see that, how this 7-segment display unit is going to be formed. Here there are different LEDs are going to be arranged. This is A, B, C, D, E, F and G1. So 7 LEDs are going to be arranged. That's why it is called 7-segment display unit. And some of the LEDs are going to be forward bias and some of the LEDs are going to be reverse bias. So whichever LED is going to be forward bias, accordingly it will display a digital decimal numbers is going to be displayed. If you consider that if the LED is having A, B, C, D, E, that segments are going to be forward bias, then it will display 0. You see here, figure 4.21 shows a 7-segment indicator. 7 LEDs labeled A through G. Here they are labeled A to G. By forward biasing different LEDs, we can display the digit 0 to 9. See figure 4.21b. For instance, to display a 0, we need to light up segment A, B, C, D, E, and F. To light up a 5, we need segment A, C, D, F, and G. So, certain segment of the LED is going to be light up, and corresponding to that, a particular decimal number is going to be displayed. You can say that 0, if it is B and C is only light up, then 1 will be displayed. If it is A, B, then D, E and G is going to be light up, then 2 will be displayed. A, B, C, D and G is going to be light up, 3 will be displayed. Here you can see that with the 6 number and with the 9 number, there are double lines is going to be shown. This double lines indicates that that particular LED segment may be light up or may not be light up. Depending upon that, it will show that this much up to this much only or up to this much only. It will display as a 6 or 9. 7-segment indicator may be the common anode type where all anodes are connected together, or the common cathode type where all cathodes are connected together. That means actually how it is going to be connected. Let us see, like this one. This is 7-segment indicator. All anodes are connected together. So it is called common anode type 7-segment indicator. Here all cathodes of the LEDs are going to be connected together. So it is called common cathode type 7-segment display unit. Segment indicator may be common anode type where all anodes are connected together, or the common cathode type where all cathodes are connected together. With the common anode type, figure 4.21 2a, you have to connect a current limiting resistance between each LED and ground, because each LED can tolerate the current from 1 milliampere to 50 milliampere, depending upon how much illumination you require and depending upon the size of the LED, it can tolerate a different amount of the current. The size of this resistor determines how much current flow through the LED. The typical LED current is in between 1 milliampere to 50 milliampere. The common cathode type of figure 4.22b use a current limiting resistance between each LED and VCC. There are two ICs, which is known as a decoder-driver. There are two ICs, 7446 and 7448. A 7-segment decoder-driver is an IC decoder that can be used to drive a 7-segment indicator. There are two types of decoder drivers corresponding to the common anode and common cathode indicators. Each decoder driver has 4 input pins, that is BCD inputs, and 7 output pins, that is A to G, which is connected to this IC. And this IC is given a BCD input, so that output will be connected to 7-segment display unit, and accordingly you can see in the figure actually. Here this is 7446 IC. This is 16-pin IC. Pin number 16 is for VCC, pin number 8 for the ground. This is TTL IC. ABCD is the BCD input. You give the BCD input. Inside the circuitry, there is a bipolar transistors are going to be utilized, which is working like a switch. So, depending upon this BCD input, some of the transistors will be on, some of the transistors will be off, and depending upon that, output of this one, that is 7 outputs will be there. Some of the outputs will be on and some of the output will be low. And depending upon whichever it is going to be low, that particular LED is going to be on and it will display that particular digits. Consider that if the BCD input is going to be 0, 1, 1, 1. So what happens? Corresponding to this, you require A, B and C. Only these 3 LED has to be on. So corresponding to that, whatever transistor here, this and this transistor will be conducting and hence VC voltage will be 0. So here it is going to be 0. So this LED will be forward bias ABC and it will display the 7. So this is called a 7446 decoder. It is decoding the BCD inputs and then it will drive the 7-segment indicator. That's why it is known as a decoder driver. But it is decoding and driving which 7-segment indicator? Common anode type 7-segment indicator. Here you have to connect externally the current limiting resistance. How much brightness you require? Depending upon the size of the current limiting resistance should be utilized. There is another type of decoder driver is also available, 7448. Here the BCD input, you can see that this is here, ABCD is the BCD input here. This is VCC and ground. There are 7 outputs which is connected to the input of 7-segment display unit. Here the cathode is common. So they are connecting directly with the anodes of each 7-segment units A to G. So here the current limiting resistance is within the IC itself. Here externally you have to connect, but here it is within the IC itself. This is that IC 7448. Figure 4.23b is alternative decoding approach. Here drives 7448 drives a common cathode indicator. Again, the internal logic converts BCD input to the required output. For example, when BCD input of 0100 is used, the internal logic forces the LED B, C, F and G to go to the conduct. The 7-segment indicator then displays the decimal number 4. Unlike the 7446 that requires external current limiting resistance, 7448 has its own current limiting resistance inside the chip itself. A switch symbol is used for the transistor actually. Switching in the actual IC is of course accompanied using a bipolar junction transistor. Thank you very much friends.